morning to all of you. Today we're going to discuss about the application of Gauss's theorem, and this application is nothing but how to find out electrostatic field due to an infinitely long and uniformly charged wire. Okay, so let us assume a wire which is uniformly charged. So we need to find out electrostatic field at any point on this side or this side. Since it is positively charged, so the direction of electric field always coming out from this, where along this direction and this direction. Okay, so let us assume that there is a distance of small r from where we're going to find out the electrostatic field. So by keeping this r is a radius, we draw a Gaussian surface, and it is a cylindrical Gaussian surface. It is a cylindrical Gaussian surface, and this is point P. Now, if this is a cylindrical Gaussian surface, it is three surfaces. One surface along this way, another one is the bottom direction is this, and another one, if you assume this, a surface direction is this. Okay, so it is something like this. Suppose this is a cylinder and this is my wire. Okay, now it is in one surface over here, another surface over here, and another surface, the body part. So this surface, the direction of the aerial vector always coming out, and direction of similarly from this surface is coming out, and the direction for this body's part always coming out of this surface, right? So according to the Gauss's theorem, E dot ds is equal to total charge divided by epsilon naught, right? So now, what is the number of electric field lines coming out from this entire cylindrical body? So that is nothing but the Gauss's theorem. So we need to find out the electrostatic field, so we are going to use this part only, right? So here, since the charges are uniformly distributed, so we assume that let lambda be the linear charge density, and it can be written as amount of charge per unit length. Assume that the length of this cylinder is small l. Okay, therefore by using this law, E dot ds, this is the amount of flux passing through this surface. Let us assume this surface is number 1. Number of flux passing through this surface, number 1 surface, and this is for the number 1, this is for number 2, and this is for number 3. And number 2, let us assume that this is the number 2 surface, and this is the number 3 surface, body part. So this is equal to Q by epsilon naught. This is a total charge. Okay. Now if you're going to see here, number 1, the angle between ds and E is a 90 degree, and for the number 2 surface, the angle between ds and E is always coming out, since it is a positive, 90 degree. So number 1 is going to be 0, and number 2 is going to be 0. What will remain? Remain the third surface. Okay, so number 1 going to be 0, number 2 is going to be 0. The third surface, why? Because the angle between ds and E for the surface of the cylinder at the body part is equal to 0, angle between E and ds. Therefore ds equal to Q total divided by epsilon naught. since cos the 0 degree is equal to 1. So this is equal to, now this ds will represent the total surface area of the whole body part. So that is nothing but the 2 pi r. R is the radius of the cylinder and the length is L. Q total divided by epsilon naught. Okay. E 2 pi r L into Q total divided by epsilon naught. Now E, that is equal to 1 by 2 pi r L. Q means what? Q is nothing but lambda into L. Lambda is the linear charge density. Okay, so this is nothing but the lambda into L. Okay, so the L get cancelled. It's equal to lambda 2 pi r epsilon naught. Now see, this electrostatic field is inversely proportional to the distance. That means what? If you go further with respect to this sphere, the electrostatic field decreases continuously. Okay. So this is the expression for electrostatic field for an uniformly charged infinitely long wire. Thank you.